EDM, Elettromeccanica di Manate, which joined the Legrand Group in May 2005 together with Zucchini, is based in the province of Teramo and employs approximately 80 people. The company designs and manufactures power transformers up to 20 megavolt amperes, with rated voltages up to 36 kilovolts, and has a production capacity of 2,200 transformers per year targeted at the European and Italian markets. These images show the vacuum resin casting and impregnation for low voltage windings. Then we can see the stocking area of the transformers ready to be shipped, and the area used to assemble the various components making up the transformer. We now move on to the testing area, including the anechoic chamber and a testing room fitted with sophisticated equipment. In particular, we can see a data control and acquisition console capable of carrying out the tests required on transformers automatically, thus preventing any possible human error. Good, here we are in EDM, Elettromeccanica di Manate, and we are welcomed by these wonderful transformers, all lined up, stock still, almost standing at attention. In particular, we are welcomed by our colleague, Mr. Franco Marini, engineer of this production unit. I would like to thank Mr. Marini very much for his time and for sharing his professional skills with us. Hi, Franco.
Hi, Giuseppe. I would like to take this opportunity to warmly welcome all the participants in the conference.
If you allow me, I have prepared a whole series of questions, and I would therefore like to immediately get to the point. The first question pops up spontaneously. Here we can see a series of resin-insulated low-medium voltage transformers. Why aren't there any oil-insulated transformers? Or rather, in the past, EDM produced oil-insulated transformers, while now it no longer does. Why is that?
We stopped manufacturing that type of transformer several years ago because oil-insulated transformers imply higher installation and maintenance costs. Moreover, they are less safe than resin-insulated ones. We aim at manufacturing high-quality and extremely safe products, and, as a consequence, we inevitably chose to produce resin-insulated transformers.
Good. Since we are talking about quality, I would like to ask Mr. Marini a specific question. What are the particular features characterizing the quality of a resin-insulated low-medium voltage transformer, and what is EDM's position in this respect?
First of all, reliability. This means that the transformer must be sized so as not to stress the insulating materials, neither from a dielectric standpoint nor from a thermal one.
Is this aimed at increasing the transformer's life?
Certainly, because a transformer's life is related to its insulating materials. The better their relative size and their operating conditions, the longer the transformer's life will be. A second feature is easy installation. This means having available a series of accessories allowing for easy installation in very different situations and locations, as well as having the possibility to transfer huge amounts of energy from the low voltage side, for example using Zucchini's busbar, which our transformer range is already equipped with. A third aspect is environmental safety. As a matter of fact, most of the products we use are recyclable. We have also designed and produced low electromagnetic emission transformers, which can thus be installed both near working environments and near or directly in contact with the electrical appliances. Another important element is operating efficiency. Indeed, EDM can optimize losses on transformers in relation to the customer's profit needs. A crucial aspect is the pre- and after-sale service, which our technical department offers to all our customers, so as to provide them with all the data required for transformer correct sizing and installation, as well as to take any preventive action on situations which might lead to problems in the long term. Thanks to all these aspects, the failure rate of our transformers is actually lower than the market average.
Another question I have for you is the following. Can we find a generally even quality on the resin-insulated low-medium voltage transformers market, or, as you mentioned, are there considerable differences?
Unfortunately, I must say that there are often unpleasant surprises. Transformers manufactured in a questionable way do exist, and this is one of the aspects leading some operators in the electricity sector to wrongly conclude that an oil-insulated transformer is more reliable than a resin-insulated one, while the opposite is actually true.
In order to verify Mr. Marini's statement regarding the poor quality of some resin-insulated low-medium voltage transformers produced by, say, not very serious manufacturers, we placed behind us some EDM transformers and some of those poor-quality transformers. In the latter, obviously, the brand has been hidden. We are thus going to carry out a comparative analysis of the various products. If you agree, I would like to focus our comparison on the two quality aspects you previously mentioned, i.e., reliability and operating efficiency.
Sure, and just as far as reliability is concerned, I would like to say a few words on the manufacturing technology which characterizes our product range in particular, making our transformers highly reliable.
We are going to use these cross-sections, aren't we?
Yes, I've prepared one of our medium voltage windings in section so as to show what it looks like inside, and some sections of transformers manufactured by some of our qualified competitors. On my left-hand side, I have prepared a medium voltage winding without the casting resin, just to show what its internal section looks like. Let us start immediately by showing our viewers what the winding consists of. This is the winding's input terminal, then the turns in the first section, then the series connection with the second section, and so on and so forth up to the tapping points. We then continue from the tapping points up to the output terminal. I would like to specify that the winding consists of one single turn per layer, and that every layer includes two insulating layers separating the upper turn from the lower one. We can observe that the voltage applied to the cables of this winding is evenly distributed along the winding's entire height and along each disc's thickness.
We can therefore say that in equal insulating conditions, the dielectric stress is constant.
Indeed, during the design stage, we are able to determine what the dielectric stress of the entire winding will be throughout its life.
And this can be seen by the naked eye looking at this winding. What happens, on the other hand, on windings by other manufacturers?
Let us take any two very common types of winding. Let's start from the first, which is the typical discs winding, in which winding sections are shaped as discs. This type is similar to one of our windings, with the exception that in one single disc, the turns are not arranged one on the other radially, with a continuous and constant potential difference, but they are layered, and each layer can include some dozen turns. This implies that the turns on one same layer have the same dielectric stress as one of our windings, but those in adjacent layers, i.e. arranged in the radial direction, do not. Why? Because the turn voltage of one layer results in a voltage at the layer ends which is 10, 15 or 20 times the turn voltage, while between the various layers, i.e. in the radial direction, the potential difference between the two conductors is a few dozen times the turn voltage.
We can therefore say that insulation is constant, but the dielectric stress and the applied voltage are not constant at all.
As a consequence, the insulating material installed between the two layers ages in a different way compared to the insulating material installed elsewhere.
What does this aging lead to in the long term?
In the long term, this reduces the material's insulating properties and consequently results in the transformer's death.
A short circuit?
A short circuit between the turns.
Any other examples?
Another example is the casual winding dropped wire technology. Here we have enamel-insulated circular aluminium conductors, while in the previous case we had tape-insulated rectangular strip conductors. In this winding, the turns are arranged starting from this position and then go up following more or less this pattern. However, since this arrangement is casual, there will not necessarily be a potential difference between two conductors. Almost certainly there will be adjacent conductors with a potential difference equal to several times the turn voltage. Two conductors can even be adjacent with a voltage which is some dozen times the turn voltage.
Therefore, this type of winding has very significant weak points,
which are totally casual. And this, because of the very high stress, in the long term can lead to an insulation failure and, therefore, a short circuit, which is exactly what took place in this case. A short circuit between two turns.
Good. Very interesting. This shows us what EDM does in terms of reliability. Now, however, let's move close to the transformers, perhaps starting from the smaller ones, if you agree.
So we can talk about thermal aspects too.
Good. Let us thus move here.
Here we have placed two small transformers.
Here we are talking about 160 kilovolt amperes, right?
Yes, these are two 160 kilovolt ampere transformers, one of which is obviously ours and the other is by an Italian competitor, to highlight the qualitative features characterizing a dry-type transformer. At first sight, the transformer produced by our competitor may look fairly sturdy and therefore better than ours from a qualitative viewpoint. However, if we took a closer look, we would notice that that is not really the case.
Looking at these two transformers, regardless of the fact that I might be biased, I would say first of all that, on the contrary, this one looks much more balanced in terms of size, starting from the wheels and the supporting structure.
Indeed, we can see that our transformer is fitted with U-shaped beam structure and with cast iron 125mm wheels, perfectly compatible with the transformer's weight,
which is 700 kilograms.
Let us have a look at our competitor's transformer, which has a very strong support structure.
You mean these sections?
Yes, these omega-shaped bars.
It is fitted with small wheels.
Certainly, they are sized for the transformer's weight, which is approximately the same. But the stamped plate 100mm wheels are surely not very suitable to handle such a weight.
So far from a mechanical standpoint, let us talk about the electrical features.
From an electrical viewpoint, going up a little we find the voltage adjustment terminal strip, where we can notice the indelible numbers pre-stamped on the winding and specified on the rating plate. Each number combination corresponds to an input voltage of the primary winding.
Conversely?
Conversely, if we look at our competitor's transformer, we can see that the adjustment ring nut is well protected. And I cannot understand against what.
Also because here everything is at hand.
Sure, the terminals are apparent, while the adjustment ring nut is protected.
I can't see any numbers here.
Exactly. There is no indication identifying the various tapping points.
Consequently, it is easier to make a mistake.
It is far easier to make a mistake. Probably the indications can be found in the instruction manual, which, unfortunately, is often lost a few days after installation.
Any other aspects?
The time has come to deal with another aspect characterizing the reliability of a resin-insulated transformer. The transformer's ability to dispose of the losses it produces and, therefore, to preserve the material's insulating capacity over time.
What are our transformer's peculiar features?
We can see that our transformer has considerably large ventilation ducts, to the point that I can insert my fingers, whose diameter exceeds 1 centimeter, into them. This allows for an easy outflow of hot air and, consequently, ensures easy transformer cooling.
What's this?
This is a PT100 probe, used to detect the low-voltage winding temperature. As you can see, we have installed it in the hottest point of the transformer.
Let's call it the critical point. Does everybody do so?
Not exactly. I must say that many of our competitors, including the most qualified ones among those represented here, install the probe at this height.
Where it is colder.
Sure, where the temperature is considerably lower, and as a consequence the display shows a lower temperature.
So one needs to pay attention to this aspect. What about this transformer in terms of cooling?
Let's see. We can immediately notice that inside it, the cooling duct size is much less than half that of our transformers.
Therefore, in case of dust build-up, they will clog.
For sure, after a few years of operation, some dust will build up, which will probably clog the cooling ducts almost completely.
Okay, regarding the windings, while as here I can see many cooling ducts.
Contrary to what I expected, I see a considerable cooling surface near the core.
And why is that?
I would say that poor quality, high-loss ferromagnetic material has probably been used, requiring a large cooling surface, while our transformer has been manufactured using high permeability and low-loss laminations.
Good. I now propose to move toward these two intermediate transformers. What are they, Franco?
Here we have two medium power transformers.
Meaning 630 kilovolt amperes.
This is our product, while the other one has been manufactured by one of our competitors and has a rated power of 800 kilovolt amperes.
Let me understand correctly, these transformers look the same to me.
Yes, I must say that in terms of shape, by and large, there are no big differences. However, I would like to focus our attention on the details we are interested in, rather than discussing the actual rated value of these pieces of equipment.
All right, let's have a look.
We can immediately see the adjustment system, where the numbers have been pre-stamped on the winding column and specified on the plate.
And in the other case?
Conversely, in this case the numbers have been simply printed on some labels, which, luckily, have not come off. Also because this transformer, manufactured a couple of years ago by one of our competitors, worked just over a week and then...
What happened?
It failed because of an electric discharge between the 20 kilovolt medium voltage winding and the low voltage one.
Therefore, this transformer is cheaper, but its value is considerably lower too.
Yes.
Let us consider some other aspects. This already does not look good to
The
me.
triangle connection looks like a make-do solution, wrapped together after combining different materials.
What else?
Then let's analyze these transformers in detail. Let us observe, for example, the natural cooling system of both transformers, which, as we said, is one of the crucial parameters determining a transformer's reliability. Here we can immediately see the low voltage winding with a large central ventilation duct, where I can insert my finger, and a duct between the core and the low voltage winding, where also a finger can go through.
Is the probe extractable again?
The probe is again extractable, located in the upper part of the winding.
In a critical area?
Exactly, in the hottest part of the product.
What about the other transformer?
In this transformer instead, we notice that there is no central ventilation duct in the secondary winding. A ventilation duct between the core and the winding.
What about this probe?
This probe is not extractable, but integrated in the winding.
Therefore, in case of
In
failure,
case of
it cannot
failure,
be
there's
replaced.
no hope.
Do these items fail often?
Sure, these probes can certainly break down. I would like to draw our public's attention to one detail. The probe is fitted with an earthed shield. The earthing shield ends in the cavity of the high and low voltage winding. Why did this transformer fail? Let's try and check the distance. You see, a finger will hardly go through, while, as you can see, two fingers can easily go through in our transformer.
Moreover, the probe is completely
The
moved to
probe
the
is
center.
completely moved to the inside and is protected by an additional surface insulator.
There are differences.
In equal-sized conditions, we could see that the insulation distances in our transformer are twice as large, just like the cooling surfaces in the low-voltage winding, which is the one exposed to the highest current. As a consequence, our equipment will undoubtedly have a far lower operating temperature and a much longer life, since the insulating materials undergo a considerably lower thermal stress compared to a not-so-high-quality transformer.
Good. We can now move to these last two, pretty big, I'd say, transformers. If you'd like to describe them?
We are now in front of two high-power transformers. More specifically, our transformer is 2,500 kilovolt amperes, while this is a transformer by one of our competitors, also with a rated power of 2,500 kilovolt amperes. Once again, we can observe some details highlighting the quality of the EDM transformer. We can immediately notice that the supporting bases are significantly larger compared to our competitor's transformer. And we'll also see that sizes which look approximately the same will in fact prove to be considerably different. Let's observe the most important aspect in a transformer capable of supplying approximately 3,600 amperes, i.e. the connections on the low voltage side. The outputs can be found on one single bar, starting from inside the winding.
Does this double bar go all the way to the end?
Yes, to the very end. It is welded along the entire height of the conductor and comes out connecting to the star connection made with a double bar, i.e. with a double contact surface, in order to minimize any additional resistance in the electrical contact.
Here we can indeed notice a largely homogeneous distribution without any weak points. Let us move on to the other one.
Conversely, in our competitor's product, we can notice that a make-do conductor comes out from inside the winding and is then butt-welded on one of the two bars, having the same size as in our transformer.
Consequently, here there is an apparent weak spot.
A weak point, which is a series welding that, theoretically, is supposed to bear approximately 3,600 amperes. Even the contact with the star center conductor is exactly half ours, although the star center conductor has two bars having the same section as in our transformer. Unfortunately, they have been positioned in the wrong way, to the point that they ensure only half the contact surface.
What about these nuts?
If we take a close look at these nuts, we can see how they have been well cooked by the transformer's overheating.
Has this transformer operated for many years?
This transformer was produced approximately 2 years ago, but it worked only for a few months, unfortunately.
Why?
Because the central low-voltage winding fused as a consequence of overheating.
Let us talk about plate rating. What is the rated weight of this transformer?
The plate of this transformer shows 5,200 kilograms, and they are real. This transformer's plate specifies a weight of 4,930 kilograms. We checked the weight and realized that this transformer's real weight is just above 4,000 kilograms.
Which is a 1-ton difference.
A 1-ton difference.
And this makes the difference also in practical terms. Well, I think this is enough. We can conclude. We have seen these interesting differences between the various transformers, and I think that Mr. Marini has effectively showed and explained that the quality of EDM medium-low voltage transformers is excellent and unquestionable. Let me, however, add a comment. Sometimes I hear people state something which is frankly questionable and wrong, i.e. that a product is not very competitive because it is more expensive than others. I would like to state firmly that competitiveness is not about a higher or a lower price. Competitiveness lies in good value for money. Therefore, a relatively high price will be dramatically balanced by high quality. As regards transformers, we have shown that reliability, long life, flexibility, limited losses and low maintenance costs are all elements which should make the designers and particularly the customers think. The customer, in particular, should shift from the concept of a short-term investment to that of a medium-long-term investment, thus duly considering all those qualitative aspects which make a real difference not only in terms of safety, but also from an economic viewpoint. We can thus conclude. Before the handover back to the studio, I have to and am pleased to thank Mr. Franco Marini for his kindness and professionalism. Thank you, Franco, and see you for the next video.
Thank you. I'd like to thank you for giving me the opportunity to explain to our viewers some of the features of our transformers. I hope you found these comments interesting.
Yes, very.
And goodbye to everybody.
Bye, and thanks again to all of you.